Hello everyone. Today we will be doing a very important chapter which is application of electrostatics. I mean till now whatever we did the concepts of electrostatics through the Coulomb's law, electric field, Gauss's theorem, electric potential, energy and different things. But today we will be directly apply these concepts into a new device that you will come to know in this class, and that is capacitors. Okay, and we'll also understand the concept of capacitors, how it can store charges and a lot of things. So before we go into those things, let us first identify what does the capacitor mean. Capacitor means where we can store charge. Till date we haven't got that kind of breakthrough in storing charges or storing electricity, but we have few things through which we can actually store charges for a while, and one of those main concepts is definitely the capacitors. And when we say that we want to store charge somewhere, okay, so when we actually want to store some charge, then whenever we are pouring charge to something, then definitely the amount of charge will increase, and correspondingly the potential of that particular space shall also increase. It's just pouring water into an empty container. Okay, just I'm giving you an analogy that whenever you are pouring charges or storing charges at a particular space, that space will definitely gather some amount of potential. So in short, we can say that amount of charge is directly known as, and you know already, this amount of charge is directly proportional to the potential that space will develop. Okay, and from here we can categorize a new expression, that is Q equals to CV, and C is equal to Q by V, and this C is known as capacitance, or the capacity of storing charges, and here it is, that is the capacity of storing charge is Q by V. Okay, so how we can define it? We can define it in a way that when the potential is 1 volt, then C is equal to Q. That means it is the amount of charge we can store to raise the potential of a particular space by 1 volt, and that amount, that quantity will define the capacitance of that particular device or that particular space. Did you understand that? That we are storing some amount of charge. So we say that when the amount of charge is enough is stored in a way that the potential is has increased by 1 volt, then the amount of charge is the capacity or the capacitance of that particular space or the device that we can say. Okay, so this is simple. I mean, we have understood what capacitance is. It is basically Q by V, and we have understood what the definition of capacitance is, and this is what, and definitely we have a unit, and the unit is, the universally in SI system is farad. Okay, is capital F, and it is farad. Okay, by through the name of the scientist farad. And since this is a very large unit, we'll come to know why this is such a large unit. I'll just explain you all just after a few things. So we use smaller units like microfarad, which is 10 to the power minus 6. We also use nanofarad, not much, but this unit is there. And the most commonly used capacitors are in the order of picofarad. These are widely used in our daily purposes, like in all the electrical appliances. It contains a capacitor at least, like television, like electric fan, motors, water purifiers, the electrified one, even the induction cooking thing, AC, everywhere capacitance is there, and there we usually use the capacitors which is in the range of picofarad, which is 10 to the power minus 12 farad. Okay, so this is the, in a nutshell, this the introduction towards capacitor, and now we'll move into the very interesting part of the concepts of capacitor, and the next part, let's check it out. So we know what is capacitance, what is its unit, and what are the attributes and all. By the time you should also write in your classwork about the dimension of capacitance. I mean the unit, the farad. What is C equals to is Q by V. So put the value of dimensions for charges and voltage, and you will find out the dimension for the capacitor or capacitance. I mean this new unit. Now we'll concentrate on the isolated spherical capacitor. Here we have, and we have drawn the diagram. Even actually also derived the thing. It's very easy. Let us just think in this way. One thing is important, that whenever we talk about capacitor, we always think about the excess charge to flow out towards the earth, so that the inner plates can have the charges intact due to the mutual electrostatic induction. And so this is again here, this earth, you can see here, this is the earthing symbol. The excess charge will flow towards the earth, so the charge will remain as it is. And here we have a spherical isolated capacitor having a charge Q and the radius capital R. So obviously potential here till the surface of the sphere, the potential remains constant. We know this from Gauss's theorem, right? So we can write potential to be 1 by 4 pi epsilon naught Q by capital R, which is the normal expression for this kind of charges. And then C is equal to Q by V. So if you divide it, it will come to 4 pi epsilon naught times of the radius of the sphere. Okay. So this is, the more the radius, more will be the capacitance. Very good. Now I was telling you just now, just before this, that 1 farad is a very large unit. Now why I was telling you, I will show you right now. Okay, so suppose this C is equal to 1 farad, not micro, I mean 1 farad. Okay, so I am writing it here. So if it is 1 farad, okay, so what is R equals to is 1 and then this. So R is equal to 1 by 4 pi epsilon naught. You know this value. You remember this 9 into 10 to the power 9 meters. Okay? Do you remember what is the radius of the earth? It was 6.4 into 10 to the power 6 meter. Do you understand? We need to have a radius of a sphere which is more than that of the earth in order to have a capacitance of 1 farad. That's why I was telling you it is impossible to have a capacitance of 1 farad on the earth, because you have the technical result for this. Okay, so we use micro, pico and all these lower things so that we can actually visualize such capacitance in practice. Anyways, now let us move into another interesting fact which is related to this, but it is the spherical shell. Okay, we have to calculate the capacitance of a spherical shell. I'll do it right now. It's very easy. So for spherical shell, you know, there will be 2 boundaries, obviously, and let us take the inner radius to be small a and the outer one to be capital B, and of course we'll have a positive charge here and a negative charge inside the outer surface, and the outer surface is earth. In order to have the flow of charge, excess charge will flow. I did one problem in potential and even in the Gauss's theorem, where we understood how the induction occurs. This charge will induce an opposite charge here, and outside there will be a positive charge which will finally flow towards the earth. In order to have the excess charge will flow, and finally these will form a spherical shell or spherical capacitor. This is an ideal situation. This is the real one. Okay, so we have to calculate the total thing. Obviously you have to understand that there is a potential difference, of course, and that is the reason why the potential difference between this surface and this surface, because they have different radii, so they have a potential difference. And what is that? Let us calculate that. The del V is, since B is more, the potential will be lesser in that way. So we have to calculate the potential difference. Here the potential doesn't remain constant, we have an earthing connection, and so the induction occurs in a different way. We have given a charge which is plus charge here only, the outside it is due to induction, so there will be a potential difference. Like here I told you that till the surface the potential is constant, but here in this case that will not remain so. These are the simple, you know, logic or simple concepts that we have to understand in order to know how things work in capacitance or electrostatics. It's simple, don't get confused, but I'm telling you that since we have 2 boundaries, we have given a positive charge in the inner boundary, and due to induction, the outer charge, inner surface of the outer periphery, it is having a negative charge and excess charge is flowing to the earth, and this way the capacitance is formed. Understand? So del V, the change in potential, I have to understand it is, if the total charge is Q, then Q by 4 pi epsilon naught, I can take common. Okay, so B is more, so the potential will be lesser, and eventually it is having a negative, so it will be on the negative side. So I'll write 1 by A minus 1 by B. So this is the expression of the potential difference that will occur in this kind of spherical shell. Okay, so now we have to calculate C, which is Q by del V, and eventually you can understand when we talk about the similar expression we did here. So finally we can write C equals to 4 pi epsilon naught Q by del V. So into, if you do the this expression, so this is the expression for a spherical shell capacitor, 4 pi epsilon naught AB by B minus A, which is nothing but the radius, the difference of radius and the product. Hope you have understood. This is not difficult. The both expressions are now open to you all. This is for the isolated spherical capacitor and this is for spherical shell. And we have calculated, even we have understood that why 1 farad capacitance is practically impossible, because we cannot form such capacitor because of the shape and size. So you understand that why we are still having this trouble of storing charges, because we require to have a huge space in order to have uninterrupted power supply and the way we can actually store charges and all. Okay, so now I'll definitely go into the next topic, which is very interesting, which is parallel plate capacitor and other things I'll come up with. So please copy these things in your class book, and then let us do the next topic. Parallel plate capacitor, the derivation is very important for board exam, as well as this particular section is very important for the numericals too. Since we are talking about the board examinations here, so I am telling you this derivation is important. We have drawn the diagram for the parallel plate. We have two parallel plates of area A, and the separation between the plates is D. You can see these are the outer boundaries, and the external one is always connected to the earth in order to have the flow of charge, excess charge will flow. Okay, so this is the diagram, and we can already understand that since we have two plates which are charged, so in between there will be an electric field, and from Gauss's theorem we know what is the amount of electric field that these two plates will have, and that is sigma by epsilon naught. Very good. We did this in Gauss's theorem. So what is electric field is sigma by epsilon naught, and sigma is Q by A. So I can ultimately write the expression of electric field to be Q by epsilon naught E. Okay, so this is the electric field. Now what you have to calculate, you have to calculate the capacitance. So for that we need to calculate the potential, and we can calculate the potential using the potential gradient. We already did in potential chapter, and what was it? It was dV dr, that is V by D is equal to E. That means this is equal to capital Q into D by epsilon naught E. So we have the expression. Now let me do it here, won't take much space. So we have the expression for potential. Great. Now we want to know C, which is nothing but Q by V. So you can easily do the thing, and it will come epsilon naught A by D. And this is the expression for the parallel plate capacitor. This is what you have to write. You have to write three, four lines. that we have a plate area A, separation is D, the electric field inside is E, the plus Q charge is stored, the earthing connection is there, so the excess charge can flow towards the earth. These things you have to write, for every derivation we have to write few lines to describe what we are going to do. So this is what we have. Now, this is purely air capacitor. That means here the medium here is air or free space. Epsilon naught means free space. Very good. But what happens if we have a dielectric? Some kind of dielectric is inserted. The dielectric constant, if I say the dielectric constant is K, then the value of the capacitance will definitely increase. Because why it will increase, I am coming to it just after a few three, four explanation. I will come to dielectrics. Right now, you understand, whenever you are inserting dielectrics within the capacitor, what happens? The capacity of that space increases, capacity of holding charges. That means it will hold more charges due to mutual induction. So the effective capacitance will increase, and that's the reason why the expression for this will be K into epsilon naught A by D. There will be some other situations. I'll come up one by one. Right now, you just know this much, that this is the expression for a capacitor, parallel plate capacitor, having completely filled with a dielectric of constant K. By the time you know that K is epsilon R by epsilon naught, that is the relative measurement between the epsilon naught for a particular medium with respect to the free space, and that is what we call K. Okay, so this is what we have in parallel plate capacitor. Now move into the sums based on this. So now we know about the parallel plate capacitor, and let us do two problems based on this parallel plate capacitor, two different aspects. These are exclusively for the board exam for class 12, but there are some tricks. Let us see. Okay, the first problem says that a parallel plate capacitor of area is 600 centimeters square, and the separation is 2 millimeter, is connected to 200 volt. We have to calculate the electric field within the capacitor and also the surface charge density, and they have given us the value of epsilon naught, which is 8.85 into 10 to the power minus 12 farad per meter. These are the data they have given, and we have to solve the problem. So we have to calculate the electric field, and you know that electric field is within the parallel plate. The way we just deduced is sigma by epsilon naught. So again we have to calculate sigma. So both way we have to face some sort of process so that we can actually calculate E without knowing sigma. Okay, so that's the thing. Okay, fine. So we know the potential, and also we know the separation. So obviously I think we can calculate the value of electric field. Electric field is potential gradient, so V by D can give me the answer, and V is 200 volt, this is given, and the plate separation is 2 millimeter, which is 2 into 10 to the power minus 3 meter. And so finally the answer would be, here it is 100 and here it is 3, so 10 to the power 3 plus 2, 5 volt per meter. This is the electric field, and similarly now we can easily calculate the value of sigma, because this is the value. Sigma by epsilon naught is the electric field inside the parallel plate capacitor. This expression we even use for deduction of parallel plate, you remember that. Okay, so we can write 10 to the power 5 is equal to sigma by epsilon naught, which is 8.85 into 10 to the power minus 12. So from here you can calculate the value of sigma, which is coulomb per meter square, will be the unit. Just calculate, find the value. I am not going to do these calculations right now. So I have shown you the process how we can calculate. So we have calculated the electric field using the concept of potential gradient, and we actually solved a sum based on parallel plate capacitor, where the electric field in between the plate exists, and the value is sigma by epsilon naught, where sigma is surface charge density. Okay, So now we'll go for the second one. The problem number 2, it says that a parallel plate is having a voltage rating of 1 kilovolt. So we have a parallel plate capacitor which is having a voltage rating of 1 kilovolt. That means it can sustain a maximum potential of 1000 volts. Okay, and it is having a dielectric which is having a value of 3, K equals to 3, dielectric constant is 3. And we are also having an electric field which is 10 to the power 7 volt per meter. They have asked us a very interesting fact. What is that? They have asked us to find the minimum area for this parallel plate so that the 10% of electric field is working and the capacitance of such parallel plate is 50 picofarad. So here they have given us a value for the capacitance. They have given us the value of the voltage rating which is maximum. It shouldn't exceed 1 kilovolt, and it is also having a dielectric slab which is having a dielectric constant of 3, and 10% of the permissible electric field which is 10 to the power 7 volt per meter can be applied in between the plates of the parallel plate capacitor. These are the data they have given us. Okay, so how we can proceed? We have to calculate the minimum area of the parallel plate, and for that reason I should tell you that we have a simple formula for that, which is this. So we may have to use this in order to solve. We know capacitance, we know K, we know epsilon naught, we don't know the plate separation though. So we can calculate this 10% of electric field. So 10% of 10 to the power 7, which is basically 10 to the power 6 volt per meter. So this is the permissible electric field that we have, and maximum voltage rating is this. So we have to calculate the minimum area and with the maximum potential. So we can easily calculate the value here. For E, we can go like this. We can, okay, let us use a different methodology. It is interesting. We can write, usually we know E equals to sigma by epsilon naught, but here we have a dielectric, so it is sigma by K epsilon naught. Okay, so, and this value is this 10 to the power 6 because this is the maximum. Okay, sigma is Q by K epsilon naught E. This is the thing. We know what we know. We know the maximum limit of electric field. So I can say 10 to the power 6 is equal to K. I don't know. That's a bad thing. But somehow I think we can calculate the value of Q somehow. How to calculate the charge? We have the capacitance, we have the potential. Okay, so Q equals to CV, right? So let us write another step here. I think that will be easier for us. So 10 to the power 6 equals to 50 picofarad into 1000 volts. So maximum I'm taking for the minimum plate area, and 3 into 8.85 into 10 to the power minus 12 into A is the unknown. And I think, my dear students, you can easily calculate the value of A from this particular expression, because everything is known here. Only the A here, you can see this A is unknown for us, which we can easily calculate, and this is your part to do this calculation and find the answer. Okay, do send me the answer in our WhatsApp AccentUs group. Alright, so now we have understood what parallel plate is, we have understood spherical shell, sphere, spherical capacitor, all these things we have known now, and also we have done problems based on parallel plate capacitor which are a bit different, and these are important for the board exam. So we have solved this. Now we should move about to a new topic in capacitance. Let's check it out. So now we already know a lot of things about capacitor, right? So now we can concentrate or we can actually see that what is the amount of energy a capacitor stores when it actually stores charges. You know, we are storing charges, the potential is getting increased, so have to know that how much energy the capacitor is holding Okay, so obviously the energy part, and you know already in the concept of electric potential that energy or is actually the work done, and in electrostatics we say that the work done is basically q dV. I mean the q is amount of charge and this is the amount of change in potential, and q dV is the total amount of work done. So if you want to know the total amount of work done for a capacitor, then this q can be replaced, or q can be replaced by CV, q equals to CV. So obviously now we can calculate the energy and we can actually integrate from 0 to V and V dV, and finally we can get the expression which is half CV square. This will give you half V square. So, and putting the limit of V and 0 will get this expression. This is the general expression for this particular capacitor. What is the amount of energy the capacitor is storing is half CV square. This is a simple derivation that comes in board exam, and I'm telling you this is a class only related for the boards. We'll come up with the inference thing in another section for capacitance exclusively. I'll do a class. So right now whatever we are doing, we are related to the things that comes in boards, okay, for class 12, and this is one of the important derivations that usually comes for 2 marks, and this is not done yet because we have to know more about it. And what is that? That suppose this CV or this C has a lot of things, okay. So if I replace C as Q by V, I mean capital Q by V, this was the elementary charge that through which we were increasing the potential here. So now we'll be using capital Q. So if C is Q by V, then this can also be written as half QV. Okay, so this is widely used. Alright, this expression is usually used when we have combination of capacitors in parallel, mostly used. This is the general form. Another one, if you write Q as V as Q by C, then also you have another expression which is Q squared by 2C. Can you see here? So we have three expressions, and this expression is mostly used for the series combination of capacitors that have come up. So parallel is here. The parallel combination, when we use this kind of expression for energy, and when we use the series one, then we use this expression for the calculation of energy or any energy losses that occur due to the combination of excuse me, capacitors. Okay, so this is the fact about energy and energy stored in capacitor. These three expressions are very important, and when they ask you to derive this form of energy, remember you have to write all these expressions explicitly. And so I hope you have understood. Now we'll move into the next topic. So when we know that we have the capacitance, we have the capacity of storing charges and everything, so it is very usual for us to combine these capacitors to gain more out of it. So we have a series combination here and we have a parallel combination here. I have already drawn the diagram, and one by one we'll do this. Okay, please copy this in your classwork and let us solve and see what happens here. Okay, so first of all, series combination. In series combination, the thing that is important to know is that in series combination, the individual charges in different capacitors which are connected in series, they will remain constant, because we should have a same charge in the system. And so individual potentials will be different, obviously. So what I can say, if the effective potential between these 2 points, if it is say V, then what I can say, V is equal to V1 plus V2, because all these individual drops will give you the total potential drop. This is from the class 9-10's concepts. It doesn't require a huge thing to know. So we know that sum of all this potential will be the total potential. So obviously what I can say is that V1 What I can write? Total charge is Q, and the effective capacitance, if it is CEQ, then V1 is Q by C1. This is, so what I'm getting? So here you have the effective expression for this particular combination, for series combination. 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 and so on. So the effective capacitance, please note it down in your class book. Effective capacitance is lesser than the least capacitor connected. Effective capacitance is lesser than the least capacitance connected. So series combination effective capacitance decreases. Okay, so this is it. What is the concept? The same charge resides to every capacitor that those are connected in series. Now we have parallel. In parallel, whenever we have parallel combination, means we have the potential which is constant throughout all the devices. The way we use our household electricity in our house, we have everything connected in parallel so that everyone gets that 220 volt 50 hertz AC connection. So parallel means common potential. All these have with the same potential, which is V. But the charges will remain different. So the total charge, if it is Q, then I can write okay, great. Then what next? What else? Q equals to CV into potential, which is V throughout. This is C1V, this is C2V, and this is C3V. So you can effectively understand that this will yield to an expression which is this. Just adding them up. So the effective capacitance increases in case of parallel combination. Effective capacitance becomes lesser in series combination. In series combination, charge remains constant. In parallel combination, potential remains constant. And this is the way we solve problems. We have other problems to do. I'll do some problems based on these concepts as well as parallel plate capacitor that I already did. So here also I'll do a few problems. We'll move into the other aspects of capacitance, and that will come up now. So now we know how we can combine capacitors in series and in parallel. Okay, that is done. But there is one very interesting fact, that is when we are actually joining capacitors in parallel or in series. You see, in series combination, I told you that charge remains constant. Potential is different for different capacitors, but in parallel combination, I told you that different charges are gathered at different capacitors which are joined in parallel, but the potential among all these capacitors remain constant. Okay, so that means we have different capacitors, we are joining them in parallel, and then what they do is they redistribute their charges to keep the potential of the main supply intact. Okay, this what happens during the parallel combination of capacitors, and here is a concept called common potential, because in parallel combination we gain a common potential. So now let us imagine that there are two capacitors, C1 and C2. They had individual charges Q1 and Q2, and definitely they had individual potentials V1 and V2. All these are there. Now they are connected in parallel. That means they are sorted in parallel, and then we have a redistribution of charges. They are connected now, so we have a redistribution of charges. Okay, so initially we have to find out that what is the total charge that is going to remain within the system if we assume there is no energy loss, no heat loss, nothing. So total charge here, you can understand, is Q1 plus Q2, and that is equal to C1 V1 plus C2 V2. This was the initial charge or the total charge that will remain within the system. Okay, so common PD is what? Total charge by total potential, total charge by total capacitance. So total charge is this, And what is the total capacitance? They are connected in parallel. So the effective capacitance for C1 and C2 will be, yes, you know already, C1 plus C2. So this is what we can say, that after this distribution of charges, when the capacitors are connected, then they actually get this kind of potential which is known as the common potential. After sharing of charges, redistribution of charges, they gain a common potential, they gain a common level, and that level is the C1 V1 plus C2 V2 divided by C1 plus C2. It may happen in some problems they give. Usually they ask that suppose if one capacitor is uncharged, very good. If uncharged means there is no charge, that is Q2 is 0, so this part will become 0, so it will be C1 V1 by C1 plus C2. Capacitance is not 0, okay, it has got a particular capacitance which is constant, but when it is, I am saying it is uncharged, that means Q is 0, potential is also 0, because until and unless we are pouring charges, there will be no gain in potential or potential energy of the capacitor. Okay, so hope you have understood this common concept of common potential. They ask you a lot of questions in board exam to find out this common PD and even find out for the energy loss. Energy loss is nothing. You have half C1 V1 square here, you have half C2 V2 square here, which is the total energy initial, and final energy will be half into C1 plus C2 into V square, that means this whole square. And if you get the difference between these two of the initial energy and the final energy, you will easily get the energy loss that you have to calculate. And these kind of problems, it comes in board exams, so do practice. Okay, I'll send you assignments, there this kind of problems will be there, so do practice those assignments and do practice the solved examples in your textbook, so that you understand these kind of concepts very easily and very clearly. Alright, now I'll move into the next topic, please check it out. So now we know about common potential, we know about the energy stored in capacitor, so let us do, it's time to do some problem again. First problem is very tricky and is based on common PD. It says that there are two capacitors, 1 mu f and 2 mu f. They can sustain a maximum voltage of 6 kilovolt and 4 kilovolt respectively, and they are connected in series. So they have asked us to find out what is the common potential. So we know already did about the parallel combination of capacitor and got the value of common PD. Now we have a different approach, that the capacitors are connected in series, but still we have to calculate the common potential. So let us approach this one. So first of all, let us calculate the charges. You know, the Q1 will be C1 V1, and that is 1 into 10 to the power minus 6 into 6 into 10 to the power 3. Q2 is C2 V2, which will be again 2 into 10 to the power minus 6 into 4 into 10 to the power 3. Whatever. What we can see here, this is smaller, alright, and this is greater between these two. So now the thing is, they are connected in series, so we know the series parallel combination, and for that reason we can actually find out the value of the effective capacitance when they are connected in series, and that is very simple. Let us do like this. So C1 C2 by C1 plus C2, and that is equal to it's 2 into 10 to the power minus 12 divided by 3 into 10 to the power minus 6, which is almost whatever. Keep it in this fashion, only 2/3 into 10 to the power minus 6 will be the answer. So 0.67 microfarad is the answer. This is the thing. So now we have two charges where this is less, Q1 is less. Here comes a new methodology, new concept. You have to understand this. Parallel, we know that the total charge we have to accumulate, but in case of series we know that the charge remain constant. And when charge remains constant, between these two charges, which charge we should take for constant? Here, the excess charge will flow. You know, in capacitor always we have a method, or we have a particular connection to earth so that the excess charge can flow. So between Q1 and Q2, it is quite obvious the lower value of the charge will be taken into consideration in order to calculate the common PD. We have the capacitor, we have the effective charge now, which is Q1, which is 6 into 10 to the power minus 3. coulomb. So this charge will be taken, and excess charge from here, which is 8 into 10 to the power minus 3, this excess charge will flow out. Okay, so great enough. And for that reason, this is the common PD we have to calculate, and common PD is given as V equals to, so here will be Q1 instead of Q, so Q1 by C, so you can put the values and get the value of this answer, which will be, in a sense, it is 6 into 10 to the power minus 3 and divided by 2/3 into 10 to the power minus 6, so you can understand it will be something around 9000 volt, and that is 9 kilovolt. So this is the answer here. 9 kilovolt will be the answer. We have calculated this sum, and you see we had a new concept here, connecting capacitor in series and then finding out the common potential, and we have also used the formula for the series combination of capacitor, and we have solved the sum. Alright, so you see every time we have to first think about the concept and then we can think about the formula. This will help you out. Now we'll come to the next problem, which is a circuit problem based on series parallel combination. We have a circuit like here, which is a bit complicated. Okay, what you can see that we are starting, and then we have a point P. From here on, capacitor is 4 mu f, and then when you're going to straight, we have another capacitor 4 mu f. Again, we have a junction here. We have another capacitor 4 mu f down, and it is connected to Q, and this is connected to R, and then we have a 5 mu f in between, and then 4 mu f. So this is the circuit. We have to first simplify this particular circuit in order to solve. Okay, so let us first simplify the circuit. Let us start from P. Okay, from P we have two junctions, one towards R and one towards S. Okay, so and it is 4, and it moves to R, and from R to Q we have another 4, and so we have got this Q again, this is P, this is R. Okay, another goes to S to Q, fine. So let us go to another one, S. We have 4 mu f between P and S, and then again from S to Q we again have 4 mu f, and now between R and S we have a 5 mu f capacitor which is in between. So this is the circuit now. Okay, sorry, this is 4. So we have redrawn the circuit, taking from here to here. Okay, now we can see the network. So what you can see here, we have a concept. Now what concept is, you see, if there is no potential difference, there will be no charge flow. So since these two are having the same ratio, that is 1:1, to this, that is also 1:1, it may be that this is 1:2, and then again it has to be 1:2. If these two are having the same ratio that of these two, then what happens, the potential drop across here and here, it is so balanced that there will be no charge flow between R and S. So this capacitor 5 mu f can be omitted. Why I am telling you? Because if these capacitors bear the constant ratio to each other, then in between the capacitor what is there, it cannot have any charge flow, because the potential drop across these two arms, PR and PS, it is balanced in such a way that no charge flows through in between. Whatever potential drop occurs, that occurs through PRQ or PSQ path. Okay, so this is the concept, and this concept we'll know more when we do current electricity. We have Kirchhoff's rule and we have Wheaton bridge. This principle is known as Wheaton bridge principle, where if the resistance or capacitance they are bearing a constant ratio, then in between capacitors or resistors they are omitted. And now you can see P to Q up loop, it is having 4 mu f, they are in series, so effective resistance is 2, and here also it is 2. So obviously we can say here that this converges to 2 mu f and this converges to 2 mu f, and finally they are in parallel. So effective capacitance is 4 mu f altogether, and this will be the answer to this particular question. So you see, solving circuit is also not easy until and unless we know the correct principle. Like this sum, you may solve other problems because you already know the formula for the series combination or the parallel combination, so you know that. But this is a special type of problem which comes in board exam, which involves another concept called Western bridge, and that's why I have shown you this, so that you can understand how we can approach this kind of problem where we can omit one capacitor and calculate the effective or equivalent from among the rest of the capacitors. Okay. So here we have come to the very important concept of dielectrics. These are the substances which are used within the capacitor, air capacitor, so that we can improve the capacity of that particular space, okay, without changing the material or something. We just add some dielectric slab and we can improve the effective capacitance. That is what happens. Now, how it happens? Dielectrics are based on certain materials or molecules which are basically polar covalent. So the molecules or the electrons which are there, paired or unpaired, they always try to polarize the neighboring charges so that to acquire more charges within them. And that's what happens here. If you imagine that these two are two plates of a capacitor or something where positive and negative charges are residing, and then we have inserted a dielectric slab here, which is this one. This is a dielectric slab, you can see, and this dielectric slab will efficiently do one thing, it will polarize. For positive we will have a negative charge column, and for negative we have a positive charge column, and effectively there will be an electric field which is opposite to the actual electric field between these two plates. So effective electric field will be like this within, after inserting the dielectric, is this. Okay. So in this way we can actually reduce the effective electric field, and in this way only we can actually find out the effectiveness with respect to the dielectric constant of this particular, which is the ratio of the electric field thus produced with respect to the ratio of the electric field, with respect to the electric field which is for the free space. It's just the ratio. Is there in your book, please go through once. This is just a concept. We have to understand how these dielectric molecules, they polarize, they get polarized due to the effect of the presence of the charges on the plates, and this way the effective capacitance of the space will increase. Okay, now I'll show you how this dielectric actually improves the effective capacitance using another diagram. So here comes another very important concept which should understand. Not only this derivation, but the concept of this derivation is very important for doing problems, especially for the sake of entrance. Okay, I'll do problems based on entrance when I'll come up with half a dozen with capacitance in few days later. But right now, let us know about the capacitor with a dielectric. I mean, there is a dielectric slab which is not inserted in full, but it is inserted with the less thickness than that of the separation between the plates. So you can see here we have a dielectric plate with the thickness of T, and the plate separation is D with the plate area A, and there are charges here, Q amount of charges, and you can see here we have fields related to the absence of dielectric within the capacitance, and there is a field here which is showing me the field developed due to polarization effect within the dielectric slab. What did I say? It is the electric field which is generated within the dielectric due to the polarization effect among the molecules of the dielectric slab and the charge which is already given to the capacitor. Okay, so fine enough. So how we can calculate here the E naught, which is the electric field in absence of dielectric? It is definitely, we have a sigma by epsilon naught is the unit, so we can directly like this. And when we talk about E, only the electric field, here we have a dielectric constant for this dielectric. If it is K, then we can directly write here it is this one. Okay, so we have this. Now you see, within this dielectric and within this areas, there are different polarization of charges and there are different charge columns which is being created out there due to the polarizing effect of the dielectric slab. Okay, so these two regions will also develop a certain amount of potential barrier, because whenever we have an electric field, whenever we have a separation, it is very true or it is very obvious that that particular region will develop certain amount of potential. Great. So if I write the total potential developed within this whole arrangement, then the potential will be due to the air, that is quite obvious, and due to the dielectric. Okay, let us write K. Okay, so what is air? How much area is there? D minus T. So potential equals to EdR, we know. So here it will be E naught and then D minus T, because this is total area, space. The separation is D minus T. And for the dielectric, it is E into T. Great. So sigma by epsilon naught D minus T plus sigma by K epsilon naught into T. This is what we have got. Now let us continue. This is the potential we are getting. We have to arrange, we can see here that we have to arrange something. We can arrange actually that sigma by epsilon naught I can take common, and then we can have D minus T as usual. But here we have, okay, let us arrange it first. D minus T plus T by K. So here again we can arrange it in better way, which is D minus T, we can take common, and 1 minus 1 by K. This is the expression we are getting for potential. And capacitance is what? Is Q by V. Okay, is Q by V. Now what is Q? Q is sigma into area by V. So finally we are getting the answer which is, so by V. So sigma by V means it is area and then epsilon naught A, because this will go up. Sigma and sigma will get cancelled, and then it is divided by D minus T into 1 minus 1 by K, and this is what the expression is. You can understand that this expression corresponds to the value of the capacitance with the dielectric having a value K, which is the dielectric constant, and this is the expression. You can see Q by V, and Q is sigma into A, because surface charge density into area of the plate will give you the total charge which was there, and this is the final expression for the capacitance including a dielectric slab. You see, the process is important. You have to understand each and every bit of concepts that actually got into this particular result. This is important. This derivation is also important for boards, but as well as the concept is very important. We have to understand how electric field develops, how potential barrier develops, and how we can actually use this using the concept of potential gradient, or V equals to E dot dr. That what we have taken or used here. Alright, so here it is. Now I'll tell you another interesting aspect of capacitor, and then I'll come up with winding up this particular class of capacitance based on boards. Okay, before we are finishing this section, which is capacitance, we'll try to do a very new and interesting one, which is a cylindrical capacitor. Mostly you'll see in our regular exercise in a lot of devices, we'll see the cylindrical capacitor only. We don't see much about the parallel plates, we see the cylindrical one. So let us see what is the expression of capacitance of such cylindrical capacitor. We have the diagram. You have understood one thing, that this is one surface where the charges will be stored, which is the radius small a, and the outer one, which is small b. The outer surface is earth, so that the excess charge flows to the earth, and the length is L. Everything is fine. Now we know that for this kind of line distribution of charges, the effective electric field according to the Gauss's theorem is E equals to lambda by 2 pi epsilon naught R. This we know. And this concept, so we are using for this particular cylindrical capacitor. So dV, the difference in potential will be E dr, E dot dr, and the angle between them is 0. So cos 0 is 1. So E dr, so E is lambda by 2 pi epsilon naught R dr. Now I will integrate to find out the net potential difference between A to B. Okay, from this surface to this surface. So integrating this, I am getting this kind of result, which I don't think you will be having a huge problem to find it out. Okay, now we have to know, since this is a Gaussian surface, so I can write lambda, Q total charge which is there is equal to lambda into L, because linear charge density, and we have that capacitance is equal to Q by V. Okay, so Q by V means lambda L by this whole thing, that is lambda by 2 pi epsilon naught log B by A and everything. So finally the expression will conclude to this form. You can understand this lambda, everything will get cancelled, and we will have 2 pi epsilon naught L, nothing else, that way divided by, we have log B by A. So this is the expression. I'm telling you, this will help you for boards definitely, but it will help more for your entrance. This expression, do remember and to practice this derivation. This is a very different type. It's almost like a problem actually. So do remember this problem. And now, since I have concluded this chapter, now it's your turn to sit back with your textbook and the classwork. Read all the short answer type questions, NCRT problems, and I'll send you assignments, solve them in our AccentUs WhatsApp group. I'll send you the assignments, we'll solve those assignments, and then we'll come up with a doubt clearing session. Alright, the usual process right now we are following during this critical days. Anyways, I hope it's not going to linger much. We'll be able to see each other in person in this room. We'll be together and do these classes. Anyways, so this is it, and I'm finishing this chapter, capacitance for boards, and again I'll come up with half a dozen with a lot of problems based on entrance, based in capacitance. Okay, till then, it's Arijit Ray telling you goodbye, and stay safe and stay productive.